Good afternoon, everyone. My name is Nada Filipovic. I'm Marketing Manager at American Wire Group. We're very pleased to welcome you to our medium voltage cables rating webinar today. Thank you very much for joining. Just a few important housekeeping items we've got. This webinar is being recorded, but a copy of the recording will be emailed to all attendees next week. At any time during this webinar, you can send us your questions by entering in your request in the questions box and selecting Send to All. Time permitting, we will answer all your questions, but if we're unable to answer any questions, we will follow up by email. And now I will pass it over to our presenter, Isaac Mueller.
Hello, I am Isaac Mueller, Applications Engineer for American Wire Group. For more than 11 years now, I've been working as an applications engineer for a wire and cable manufacturer, focusing on wire and cable applications in the United States and Canada. Currently, I am a voting member on the Canadian Electrical Code Executive Committee in Part 1, representing wire and cable manufacturers. I am Section 4 Chair for Conductors and Ampasties and Section 12 Vice Chair for Wiring Methods. I continue to be active in these positions on the Canadian Electrical Code committees. I am also a member of several task groups and working groups for the Canadian Electrical Code. Over the past decade, I've been actively participating on UL and CSA standards committees, focusing on how wire and cable is manufactured, tested, and marked. Although I have been focused on manufacturing, I also have practical experience in determining the right wire or cable for many different applications, with a focus on NEC or Canadian Electrical Code compliance. As a professional electrical engineer working for a wire and cable manufacturer, my primary role has been to run several different calculations for ampacity, conductor operating temperature, impedance, and other factors, often using software such as SimCap and PLS-CAD. Let's get started. For nearly 20 years that American Wire Group has been operating, thinking customer has been at the heart of our core values. Our core values shown here are what our team practices daily. We believe this is what makes us the strong company that we are today. Our continually growing range of wire and cable products emphasize our focus on servicing our customers' needs. We have overhead conductors to cover your overhead transmission and distribution system needs. Our medium voltage power cables are rated 5 kV to 46 kV with fully water block stranded conductors meeting or exceeding industry requirements. We use only the highest grade EPR and TRX LPE insulation compounds for a worry-free medium voltage cable system. Although our focus is on concentric neutral or round wire metallic shields, we also have flat copper tape or flat copper strap metallic shields, should your need for these systems arise. With a 90 degrees Celsius or 105 degrees Celsius continuous conductor operating temperature rating and an available crosslink polyethylene jacket, you are guaranteed to get a medium voltage power cable that meets or exceeds the needs of today's demanding installations. We also carry a wide range of low voltage cable systems, including substation and battery storage cables. The cables that we offer are listed, certified, or qualified in accordance with UL, CSA, ICEA, or ASTM standards, making them suitable for installation and use in the United States or Canada. During this presentation, we'll take a brief look at medium voltage power cables and compare some of the more popular options available in the market. We will review some of the content of the last webinar regarding medium voltage power cable constructions, followed by a recap of what standards are typically used for medium voltage cable constructions for installations in the United States and Canada. We will look at the typical applications for these cables in the utility, renewable, and building markets. Conductor types and terminations will be introduced. Standard North American voltage classes and insulation levels will be reviewed, followed by a few key details regarding the insulation systems used today: tree retardant crosslink polyethylene and ethylene propylene rubber. The three more common metallic shields will be defined and compared, providing a few selection criteria for each. We have selected to review the three more common jackets available today, which cover both thermoplastic and thermoset material types. We will introduce the various conductor and cable water blocking technologies available. Finally, the application markings and ratings will be discussed. We will finish this presentation off with a summary, followed by an opportunity to ask any questions that you may have, time permitting, of course. During our last medium voltage cables presentation, we discussed the various standards used in the market today. The physical and electrical characteristics for EPR and TRX LPE were compared, demonstrating that the EPR insulation is more flexible, while the TRX LPE insulation has lower electrical losses. Most other insulation ratings are comparable. The more common metallic shields available today were described and compared. We'll review this again, adding a few details regarding concentric neutral sizing and phase conductor ampacity comparisons for various concentric neutral configurations. The three more common jackets were reviewed. Again, we will have a similar comparison in this presentation. As we had seen last time, there are several medium voltage cable standards that define how these cables are manufactured, tested, and marked. There are several options available in each standard so that a cable could be manufactured to have a long service life for a particular installation. In the United States, there are several Insulated Cable Engineers Association or ICEA standards, as well as an Underwriters Laboratories or UL standard for medium voltage cables. The ICEA standards focus on cables for utility applications, while the UL standard focuses on commercial and industrial applications falling under the National Electrical Code or NEC. In Canada, there are two Canadian Standards Association or CSA standards for medium voltage cables covering utility and building wire applications falling under the Canadian Electrical Code or CE code. There are two ICEA standards for water blocked conductors and cables. CSA C68.5 also mentions an optional connectability test for water blocked stranded conductors, which is the current cycle test from ANSI C119.4. Medium voltage power cables are installed and used in a variety of applications. Utility applications are among the most common, as these cables were primarily intended for utility use. Quite often there will be a transition from overhead power lines to underground cables. In this case, the medium voltage power cable is installed down a pole, usually in conduit for mechanical protection. With the growth of renewable generation projects comes the ever-demanding need for more cost-effective wire and cable installations. Since timelines are usually tight, as are the budgets, these cables are commonly direct buried on these sites. Medium voltage power cables in building applications are typically installed in cable tray or pulled into conduit. For cable tray installations in building applications, these cables must be rated and marked accordingly. In the United States, this marking would be for CT use, while in Canada, the marking would be TC. Medium voltage power cables are available with copper or aluminum phase conductors, while the metallic shielding components are typically copper. Copper phase conductors are either compressed or compact stranded. Aluminum phase conductors are available in a wider size range than for copper due to the difference in conductivity for aluminum versus copper. As with copper, these conductors are either compressed or compact stranded. Sizes 1250 kc mil and 1500 kc mil are compressed stranded only. Aluminum conductors are also available as solid conductors for smaller conductor sizes. Compression lugs and shear bolt terminations are generally designed for use with Class B stranded conductors that conform to ASTM, concentric, compressed, or compact stranded conductor sizes. Where there is any doubt, the compression lug manufacturer should be consulted to verify the selection of an acceptable compression lug. Mechanical lugs are usually designed to accommodate a wide range of conductor sizes, so stranding type is usually not a problem. The medium voltage concentric neutral power cable standard in Canada, CSA C68.5, references the current cycle test from ANSI C119.4 in Annex I. Specifically, this test is referred to as the connectability test for blocked strand conductors. Within this annex, it is stated that there are many factors which can affect the performance of the compression lug. Most importantly, the selection of connector, compression tool, die, and crimping technique should be as per the recommendation of the connector manufacturer. The voltage ratings for medium voltage power cables range from 5 kV to 46 kV. In the United States, 46 kV is used only for renewable generation systems. Medium voltage power cables employ a shielded insulation system, so there is an insulation level applied with the voltage rating. The insulation level is generally selected based on the fault clearing time of the protective device. Many medium voltage cable manufacturers only make insulation systems with 100% and 133% insulation levels. If a 173% insulation level is required, then the next higher voltage class should be considered. Another reason to select a higher insulation level may be the presence or likelihood of voltage spikes. A popular example is the application where the insulated power cable ties into overhead power lines. Lightning strikes are possible, so a higher insulation level may be desirable. The two key medium voltage cable insulations are tree retardant crosslink polyethylene, or TRXLPE, and ethylene propylene rubber, or EPR. TRXLPE is commonly used in Canadian installations, as well as renewable generation systems in the United States. EPR is commonly used in installations in the United States and some building wire applications in Canada. EPR is also commonly found in oil and gas exploration and processing installations. Since TRXLPE and EPR are both thermoset insulation systems, the maximum temperature ratings can be the same. 105 degrees Celsius has been the typical normal conductor operating temperature rating for EPR insulated power cable, while it's becoming more typical for TRXLPE insulated medium voltage power cable. Note that even though the normal operating temperature may be either 90 or 105 degrees Celsius, the maximum short circuit temperature is 250 degrees Celsius. With a higher maximum operating temperature, the maximum continuous current is higher, but either the maximum short circuit current is lower or the short circuit duration is shorter. The difference in short circuit current between 105 and 90 degrees Celsius rated cable is 6%. To properly distribute voltage stress in the shielded medium voltage insulation system, a metallic component must be applied in direct electrical contact with the insulation shield. This metallic component is referred to as the metallic shield and is typically one or a combination of the following: round bare copper concentric neutral wires, rectangular bare copper concentric flat straps, or flat bare copper tape. Other metallic shield possibilities include corrugated copper tapes, tinned copper components, or lead sheath. Our focus will be on the typical metallic shield constructions. This metallic shield component also provides a ground fault current path, a grounded outermost cable component for safety, and contains the electrical interference that would otherwise affect adjacent cables and systems. Concentric neutral wire shields usually consist of solid, round, bare copper wires, the total size of which is based on the conductivity of the phase conductor. A concentric neutral wire shield may also be sized based on the short circuit requirements of the system. Medium voltage cables with a full concentric neutral are typically used in single phase applications. For three-phase 4-wire applications, A 1/3 concentric neutral for each cable is used altogether, resulting in a full system neutral. Likewise, 3-phase, 4-wire reduced neutral configurations are also possible. Typical applications include residential pad mount transformers, as well as utility, commercial, and industrial distribution and services. Concentric neutral cables are also widely used in renewable generation applications such as wind and solar farms, where the concentric neutral is sized based on fault current carrying capabilities. The concentric neutral configurations shown here are based on conductivity. The top table is for full concentric neutral configurations where the concentric neutral has approximately the same conductivity as the phase conductor. The bottom table is for 1/3 concentric neutral configurations where the concentric neutral has approximately 1/3 the conductivity of the phase conductor. There are many concentric neutral configurations that could be manufactured to achieve the same concentric neutral size. For example, a medium voltage concentric neutral power cable with a 1/0 aluminum phase conductor and 16 14-gauge concentric neutral wires would be the same as a cable with a 1/0 aluminum phase conductor and 10 12-gauge concentric neutral wires. There will be a slight overall cable diameter difference, and the concentric neutral spacing will be different. However, they're essentially the same cable. If the concentric neutral wires are bonded at both ends of the cable, then there will be a circulating current within these wires. This circulating current will be proportional to the phase current, but will be limited by the resistivity of the concentric neutral wires. This circulating current will cause the concentric neutral wires to be a source of heat and will have a negative effect on the current carrying capability of the phase conductor. So, a smaller concentric neutral size will have a higher resistance, limiting the circulating current, thereby reducing the impact on the phase conductor current carrying capability. In cables with smaller sized conductors, this is not so evident. For larger sized cable, however, it can make a significant difference. The tabled values shown here help to illustrate this point. Flat strap shields usually consist of solid rectangular bare copper straps, ranging in size depending on the manufacturer. As with a round concentric wire shield, the size is typically based on conductivity, but may instead be based on a minimum specified short circuit capability. Medium voltage cables with a flat strap neutral are typically used where a smaller diameter alternative to concentric neutral power cable is required. Replacement of an existing installation of paper insulated lead sheathed cable or PILC in underground duct is a prime example. Although medium voltage cables with a flat strap neutral are more difficult to strip and terminate compared to modern concentric neutral power cables, they are easier to install compared to PILC. They are also a cost-effective and environmentally friendly solution to PILC. Flat copper tape is also another option for the metallic shield component. Where a 5 mm thick uncoated copper tape of a specific width is applied helically around the insulated conductor with a minimum 25% overlap. This overlap is defined such that when the cable is bent, the copper tape overlap will not separate, maintaining its electrical contact, minimizing the net metallic shield resistance. Since the resulting neutral size based on conductivity is small, this shield option is usually specified for use in a 3-phase, 3-wire system where a neutral conductor is not required as part of the system. As such, the short circuit current carrying capability or duration is significantly lower than that of a concentric neutral wire or flat strap shield. Typical applications include utility, commercial, and industrial distribution and services. A medium voltage cable jacket is selected based on the application to protect the cable from the installation environment, allowing the cable to achieve a long and worry-free service life. The cable jacket may be overlying, where it is extruded into a tube over the metallic shielding layer, or extruded to fill, meaning that it is extruded over top of and in between the metallic shield components. This is quite often done with concentric neutral wire shields in one pass so that the individual wires do not move when the cable is handled. Extruded to fill jackets also fill the void between the concentric wires so that in case of a compromised jacket, water cannot easily migrate down the length of the cable. Water blocking additives such as water soluble yarns or powders can also be used under the jacket to prevent water migration. Of the many cable jacket possibilities, the three most common for medium voltage cables are PVC, linear low density polyethylene, and crosslink polyethylene. The thermoplastic jacket limits the underlying metallic shield component short circuit temperature to 200 degrees Celsius. This would apply to PVC and linear low density polyethylene jackets. For thermoset jackets, such as crosslink polyethylene, the shield short circuit temperature would be limited to 350 degrees Celsius. To illustrate the effect of short circuit temperature rating of the jacket, we will look at a few examples. For the first example, we will consider a 500 kc mil aluminum cable rated 35 kV with 100% insulation level, TRX LPE insulated and rated 105 degrees Celsius, with a concentric neutral consisting of 16 12-gauge bare round copper wires, jacketed with either a thermoplastic or thermoset material. When a thermoplastic jacket is used, such as linear low density polyethylene or PVC, the maximum concentric neutral short circuit temperature would be 200 degrees Celsius. Alternatively, when a thermoset jacket is used, such as crosslink polyethylene, the maximum concentric neutral short circuit temperature would be 350 degrees Celsius. This would result in a significant increase versus the thermoplastic jacketed cable. Note that these values shown here, especially the temperatures, as well as the calculation methods, are as indicated in ICEA P45-482. For the second example, we will consider a 500 kc mil aluminum cable rated 35 kV with 100% insulation level, TRX LPE insulated and rated 105 degrees Celsius, with a 1/3 concentric neutral sized based on the short circuit capability, with a thermoplastic jacket as the reference. When a thermoplastic jacket is used, such as linear low density polyethylene or PVC, the maximum concentric neutral short circuit temperature would be 200 degrees Celsius. Since this is the reference design, the 1/3 concentric neutral is sized based on conductivity, resulting in 16 12-gauge bare round copper wires. Alternatively, when a thermoset jacket is used, such as crosslink polyethylene, the maximum concentric neutral short circuit temperature would be 350 degrees Celsius. To meet the similar shield short circuit requirement as compared to the thermoplastic jacketed cable, the concentric neutral configuration could be 11 12-gauge bare round copper wires. The result is that when a crosslink polyethylene jacket is used on a medium voltage concentric neutral power cable, where the concentric neutral wires are used only for short circuit current carrying capability, then the concentric neutral copper content could be reduced. There are many medium voltage power cable water blocking technologies available today, from the traditional pumpable strand filler compound to water soluble powders, tapes, and yarns that swell on contact with water to prevent water migration down the voids of the cable. These water blocking methods are generally verified using ICEA test methods to withstand a minimum of 5 psi of water pressure. Many medium voltage power cable customers, however, are insistent on meeting a 15 psi requirement. When the water blocking method is employed within the stranded conductor, care must be taken so as not to interfere with or contaminate the semiconducting conductor shield layer. This has been an issue with some pumpable strand fillers. Water swellable tapes and yarns are becoming more and more common as a preferred water blocking system within the stranded conductor. With no change in the overall conductor diameter and conductor resistance, standard terminations such as compression lugs are not a problem. The water blocking method employed directly under the cable jacket is typically a combination of water-soluble powders, tapes, and yarns. Since these water blocking systems are quite thin, there's no significant change in the overall cable diameter. There are many different markings and ratings that can be applied to medium voltage power cables. For many applications, direct burial and sunlight resistant markings are all that is needed. This is typically all that is required in utility and renewable generation applications in the United States. However, in Canada, the added low temperature marking LTGG is generally required. This added marking indicates that the cable has been tested for cold impact and cold bend at -40 degrees Celsius. Building wire applications will usually require a cable tray marking for CTUs when installed in accordance with the NEC in the United States, or TC when installed in accordance with the CE code in Canada. These medium voltage tray cables are typically copper tape shielded with a PVC jacket and may be marked FT4 for use in a building. In summary, in this very brief presentation, we reviewed the many different medium voltage cable standards available which define cable constructions for commercial, industrial, and utility applications in the United States and Canada. The available conductor types were introduced along with the various voltage classes and insulation levels for these cables, with the selection criteria for each. The ratings and applications for the two key insulation systems were compared. The three most common metallic shields were compared with a focus on concentric neutral sizing. A few reasons for selecting each type of metallic shield were provided. The three most common medium voltage cable jacket materials were compared, focusing on the applications for each, along with the shield short circuit current limitations. Various water blocking technologies were introduced, and the generally available application markings and ratings were shared, with the more common markings and ratings identified.
Thank you, Isaac. We will go ahead. We have a few minutes for some questions, so feel free to go ahead and enter those questions in the box. I'm hitting send to all, and we'll answer as many as we can before the time is up. One more. Do you provide something like a CPD certificate of completion?
I think we may need some more details on what the requester means by the CPD certification. So if you can email us some details regarding the basis of this question, I think we can definitely give you an answer on this. Thank you.
Okay. What type of shield do you recommend for utility scale solar plant application?
For utility scale solar plant applications, we've seen quite a bit of concentric neutral power cable being used. And like we had stated during the presentation, the idea of the concentric neutral is that it's there for fault current carrying capabilities. So we're seeing both in wind power and solar applications, concentric neutral sizes ranging from 1/3 all the way down to 1/8 or 1/12. Very dependent on the application, very dependent on the fault current carrying requirements of the system. So some get very custom and others not so custom and stick to the 1/3, 1/6. So it ranges quite widely. Concentric neutrals are generally the cable of choice in renewable applications.